Welcome back to Reflection. I'm Daniel, and in this video we're going to continue where we left off in the last video, and we are going to discuss reflection in the context of type erasure, which is a big problem on the JVM. Okay, so we are in the same application that we started in the last video, and here we are going to talk about type erasure and how to bring it back with the Scala reflection API. So as you know, generic types are erased at compile time. Now the reason is historical and has to do with the JVM philosophy, which is that Java must be backwards compatible. So Java 5 introduced this very nice concept of generics with the primary goal of type checking collections. So Java pre-version 5 did not have generics, so the Java 5 compiler basically erased those generic types to maintain backward compatibility to the old JVM bytecode. As a consequence, all JVM languages which implement some form of generics, like Scala for example, have to go through the same type erasure process. There are two big pain points with type erasure. Let's call this pain point number 1, the fact that you cannot differentiate between generic types at runtime. So for example, and I gave this example in the beginner's course, but I'm going to restate it here. Let's say for example I have a val numbers, for example, which is a list of ints like 1, 2, 3. Well, if I do numbers match and I put two cases here, let's call this first a list of strings, which is of type list string, and in this case we're just going to print line list of strings. Let's put our little arrow here. And another case, let's call this list of ints, or a list of numbers, which is a list int. And in this case, printing list of numbers. Well, if we run this code, we are going to get into the very interesting situation where we print to the console a list of strings, although numbers is a list of int. That's because at compile time, the generic types are erased. So basically the pattern match here becomes list of strings of type list and list of numbers of type list. Now the Scala compiler doesn't allow us to do that, but from the point of the runtime, this is actually what it boils down to. So we have a case which is a list and a case which is a list. Well, of course, the first pattern is going to match, which is a list of strings, and that's why we see a list of strings printed to the console. Let's add the types back. And notice here that the compiler, the IDE gives us a hint, says fruitless type test, a value of type list int cannot also be a list string, but still might match its erasure. So this is pain point number 1. Pain point number 2 is that we have some limitations on overloads. So for example, if we have, for example, a method called process or process list, which takes a list of, say, int, and just returns a number, say 42, and we have another method called process list, which takes another list of type string, we would normally consider that an overload, but from the point of the runtime, it's not. Because this list type will get erased in the generic. So basically the two methods after compilation, they will get reduced to list of type list and list of type list. So basically these two methods have an identical definition post compilation. So that's why the compiler doesn't allow us to do that. And unless we resort to some other kind of workarounds, for example, the magnet pattern, if you remember from the implicits chapter, then we're stuck with this pain point, with this limitation on overload. So this is painful. Now, given all of this, Scala has a reflection API workaround which allows carrying the complete generic time available at compile time to the runtime. Enter type tags. So let's see how we can use these. First of all, step number 0, do the right import. And the import that we're going to say is import the universe dot underscore. Remember the universe that we imported earlier, Scala reflect runtime universe? Well, we are going to import everything within that thing. in order to use type tags. And having this imported, we can create a type tag by saying, let's call this t tag equals type tag of type, let's say person. And type tag is a method which takes an implicit type tag and just returns that tag. This works the same as the implicitly method, and this will return a type tag instance for the type person. And having access to a type tag then allows us to use whatever has been defined in this type. For example, let's print line, for example, ttag dot TPE. This is the fully qualified name of this tag. And if we run this, we are going to see the fully qualified class name of person. So we see lectures part 5 TS reflection person. So creating a type tag is done by the compiler, and the information contained within that type tag is carried to the runtime, and by accessing the TPE method or calling the TPE method, then I have access to a type instance. Look at this little thing. Now, type tags aren't really useful by themselves. Type tags are basically used as a type evidence, which then allows us to inspect generic types. Let me give you an example. Let's say I have a little class, let's call this myMap, which takes two generic parameters like key and value. Okay, and assume some kind of implementation, but we don't really care. We just care about the type signature here, myMap, which takes two generic parameters. Now, for example, if I define a method called getTypeArguments, which takes a type t and a value of that type, and besides the value of the type, I pass in an implicit type tag, which is of type tag with t. This is created by the compiler when it does the implicit inference. Okay, then we can say type tag.tpe. Notice that this guy has the type runtime.universe.type, which contains all the type information contained within the t type. So already we have the capability of inspecting a generic type at runtime, and we can simply say, for example, match. We can pattern match on a type. And I'm going to decompose this into what's called a type ref. This guy takes 3 arguments. If we look at the unapply method here, we can see that this type ref thing returns an option of 3 things: the whole type itself, the symbol, which is a description as we saw earlier in the last video, and the list of type. Now this guy is the generic type that's actually used at runtime. So this is how we carry the information from the compile time to the runtime by calling unapply on an inferred type here from the type tag. So type tag.tpe, which is of type ref, and this receives something, a symbol, and a list of something, a list of generic parameters. Let's call this type arguments. Okay, let's just return them, type arguments, and in case we have something else, let's just return an empty list. Okay, so this, notice that the getTypeArguments method returns a list of runtime universe.type. This is the list of the generic parameters that the t type was decorated with. So if I instantiate, for example, a myMap with, say, an int and a string, so say val myMap, which is a new myMap with, say, int and string, then my desire here is to have access to these 2 types at runtime by calling, let's call this type args, get type arguments with myMap. And of course the compiler will create an implicit type tag of type myMap int string. So basically the compiler says, okay, this will pass in a type tag which is of type tag of myMap of int and string. So remember, the type tag can carry the generic type information to the runtime. So the compiler creates this for me, and at runtime, when I call the getType arguments, then I get access to the TPE member of the type tag that the compiler created originally, and then I do a pattern match on that, and then I decompose it into something and the type arguments. So I have access to the type arguments at runtime. Say, for example, I print them out. So if I print the type args, let's see what we get. So we get a list of int and string. Now, I know this is a little bit too magical, so you may wonder, how on earth does the t not get erased in the first place? Never mind the int and string. Why is not the my map erased in the getType arguments method at the moment we call it? Well, at compile time, the compiler creates this little type tag for us, which has some internal data structures, including this TPE thing, which can carry out the information of the types at runtime so that we can later inspect them. So the types can safely be erased after compilation, but the type tag object here, which is going to get passed at runtime, will hold the information that we want, and we can later use that information if we want to, for example, print that out. Now, because we have access to the erased type information at runtime through these little data structures that the compiler creates before compiling the code, we can do a bunch of checks and operations. For example, let's call a method, say, is subtype, which takes two generic type parameters, a and b, and tests whether a is a subtype of b. Let's add some implicit type tags. Let's call this t tag a, which is a type tag a, and t tag b, which is a type tag b. And this returns a boolean. And the implementation here is going to be simply t tag a dot TPE. Notice that this TPE returns an instance of this very cute type abstract thing. Now, this type TPE has a very interesting method called less than the other TPE, like t tag b dot TPE. So if I say, for example, class animal and class dog extends animal, I can simply print line, for example, is subtype with dog and animal. So if I run this, notice what I'm going to see. Well, I'm going to see the value true here. And that's because the compiler, when I use the method is subtype with dog and animal, the compiler takes care to construct these type tags at compile time before the types are erased. And after the types are erased, the type tags, even though their own types are erased, their own data structures are correctly filled so that these methods, such as, for example, the less than colon less than, can act correctly. So type tags are basically Scala's way of simply making do without the erased types. So let's recap for a little bit. This is step one of creating a type tag. Let's call this manually. But the preferred way of using type tags is to pass them as implicit parameters. So step, let's call this 2. Pass type tags as implicit parameters. And the compiler will take care to create them for us. And then we can do all sorts of checks and operations with them once the compiler has access to the type tag instances. Okay? Now, one last thing that I want to show you is that these type tags can be very sweetly linked to the other reflection API that we talked in the last video. Let's run through an example, and I'm going to copy the invoking by name case. So I'm just going to simply copy this code, and I'm going to replace the essential bits. So we have a person called Mary, and I also have the method say my name, so I'm just going to remove these. Reflecting the instance is also not needed because the method symbol that I want to create here is, instead of calling the universe called universe.typeOfPersonDeclare, notice that this typeOf method returns a type instance. So I can simply say type tag person.tpe, which is a member of the type tag instance. And it still returns a type instance. So let's call this another method simple. So instead of saying universe.typeOfPersonDeclare, we can instantiate a type tag and call the TPE method on it. Now, of course, once we get the method symbol out of a type tag, we can use that as an argument to reflect method. Of course, this relies on the reflected instance. Okay, so let's call this same method. So this is basically just another way of getting the method symbol, which is one of the steps in the reflection pattern that we used in the last video. This is just one way, and the RU type of person is another way. Okay, and of course we can call same method .apply, and we are going to see hi, my name is Mary printed to the console, just as we had in the last example. So see, we have hi, my name is Mary again. Alright, so now you know more about the Scala Reflection API. Now, the API and the type tags, as we've seen in this video, will cover almost all of the cases where you would need reflection. Anything more complex and you will get into metaprogramming, which is a really, really deep rabbit hole. I'm Daniel, and I will be waiting for you in the next video.